This is the INCOSE Systems Engineering Handbook, Chapter 3, Section 3.6 video, the Introduction to Case Studies. Chapter 3 is the generic life cycle stages, and this is the final section. So, Section 3.6, Introduction to Case Studies. Real-world examples that draw from diverse industries and types of systems are provided throughout this handbook. 5 case studies have been selected to illustrate the diversity of systems to which systems engineering principles and practices can be applied. Medical therapy equipment, a bridge, a super high-speed train, a breach of a cybersecurity system, and a redesign of a high-tech medical system for low-tech maintenance. They represent examples of the failed, successful, and prototype systems that all define the state-of-the-art. These studies may be categorized as medical, infrastructure, and transportation applications. In the manufacturing and construction industry domains, with and without software elements, complex and subject to scrutiny in the concept, development, utilization, and support stages, as all have a need to be safe for humans and are constrained by government regulations. 3.6.1 Case 1 Radiation Therapy, the THERAC 25. Background 3611 THERAC 25, a dual-mode medical linear accelerator, LINAC, was developed by the Medical Division of the Atomic Energy Commission Limited of Canada, starting in 1976. A completely computerized system became commercially available in 1982. This new machine could be built at a lower production cost, resulting in lower prices for the customers. However, a series of tragic accidents led to the recommended recall and discontinuation of the system. The THERAC 25 was a medical LINAC, or particle accelerator, capable of increasing the energy of electrically charged atomic particles. LINACs accelerate charged particles by introducing an electric field to produce particle beams, i.e. radiation, which are then focused by magnets. Medical LINACs are used to treat cancer patients by exposing malignant cells to radiation. Since malignant tissues are more sensitive than normal tissues to radiation exposure, a treatment plan can be developed that permits the absorption of an amount of radiation that is fatal to tumors, but causes relatively minor damage to surrounding tissue. 6 accidents involving enormous radiation overdoses to two patients took place between 1985 and 1987. Tragically, 3 of these accidents resulted in the death of the patients. This case is ranked in the top 10 worst software-related incidents on many lists. Details of the accidents and analysis of the case are available from many sources. 3612 Approach. THERAC 25 was a revolutionary design compared to its predecessors, THERAC 6 and THERAC 20, both with exceptional safety records. It was based on a double-pass concept that allowed a more powerful accelerator to be built into a compact and versatile machine. AECL designed THERAC 25 to fully utilize the potential of software control, while THERAC 6 and THERAC 20 were built as standalone machines and could be operated without a computer. THERAC 25 depended on a tight integration of software and hardware. In the new tightly coupled system, AECL used software to monitor the state of the machine and to ensure its proper operations and safety. Previous versions had included independent circuits to monitor the status of the beam, as well as hardware interlocks that prevented the machine from delivering radiation doses that were too high or from performing any unsafe operation that could potentially harm the patient. In THERAC 25, AECL decided not to duplicate these hardware interlocks since the software already performed the status checks and handled all of the malfunctions. This meant that the THERAC 25 software had far more responsibility for safety than the software in the previous models. If, in the course of treatment, the software detected a minor malfunction, it would pause the treatment. In this case, the procedure could be restarted by pressing a single proceed key. Only if a serious malfunction was detected was it required to completely reset the treatment parameters to restart the machine. The software for THERAC 25 was developed from the THERAC 20's software, which was developed from the THERAC 6's software. One programmer, over several years, evolved the THERAC 6 software into the THERAC 25 software. A standalone real-time operating system was added along with application software written in assembly language and tested as a part of the Thirac 25 system operation. In addition, significant adjustments had been made to simplify the operator interface and minimize data entry, since initial operators complained that it took too long to enter a treatment plan. At the time of its introduction to market in 1982, Thirac 25 was classified as a Class II medical device. Since the Thirac 25 software was based on software used in the earlier Thirac 20 and Thirac 6 models, Thirac 25 was approved by the Federal Drug Administration under pre-market equivalency. 3.6.1.3 Conclusions. The errors were introduced in the concept and early development stages, when the decisions were made to create the software for Thirac 25 using the modification of existing software from the two prior machines. The consequences of these actions were difficult to assess at the time, because the starting point, software from Thirac 6, was a poorly documented product, and no one except the original software developer could follow the logic. This case illustrates the importance of the off-the-V core studies early in development. The issues from the Thirac case are, unfortunately, still relevant, as evidenced by similar deaths for similar reasons in 2007 upon the introduction of the new LINAC-based radiation therapy machines. 3.6.2 Case 2. Joining two countries, the Øresund Bridge. 3.6.2.1 Background. The Øresund region is composed of eastern Denmark and southern Sweden, and since 2008 has been linked by the Øresund Bridge. The area includes two major cities, Copenhagen and Malmö, has a population of 3 million, and counts as Europe's 8th largest economic center. 1/5 of the total Danish and Swedish gross national product is produced in the region. The official name of the bridge is translated as the Øresund Connection to underscore the full integration of the region. For the first time ever, Sweden is joined permanently to the mainland of Europe by a 10-minute drive or train ride. The cost for the entire Øresund connection construction was calculated at 30.1 billion DKK, or $3 billion US. The investment is expected to be paid back by 2035. The Øresund Bridge is the world's largest composite structure, has the longest cable-stayed bridge span in the world carrying motorway and railway traffic, and boasts the highest freestanding pylons. The 7.9 kilometer, 5-mile long bridge crosses the international navigation route between the Baltic Sea and the North Sea. A cable-stayed high bridge rises 57 meters, 160 feet, above the surface of the sea, with a main span of 490 meters, 0.3 miles. Both the main span and the approach bridges are constructed as a 2-level composite and steel concrete structure. The upper deck carries a 4-lane motorway, and the lower deck carries a 2-track railway for both passenger trains and freight trains. The rest of the distance is spanned by the artificial island Peberholm, Pepper Islet, named to complement the Saltholm Islet to the north, and a tunnel on the Danish side that is the longest immersed concrete tunnel in the world. Since the completion, Peberholm has become a natural habitat for colonies of rare birds, one of the largest of its kind in Denmark and Sweden. Nations other than Denmark and Sweden also contributed to this project. Canada provided a floating crane, aptly named the Swan, to carry prefabricated bridge sections out to the site and place them into position. 49 steel girders for the approach bridges were fabricated in Cadiz, Spain. A specially designed catamaran was built to handle transportation of the foundations for the pylons, which weighed 19,000 tons each. The approach, 3.6.2.2. As noted in many histories of bridge, the development stage of the project began with well-defined time, budget, and quality constraints. The design evolved over more than 7 years from start to delivery of final documentation and maintenance manuals. More than 4,000 drawings were produced. The consortium dealt with changes as necessary using a combination of technical competence and stakeholder cooperation. Notably, there were no disputes and no significant claims against the owners at the conclusion, and this has been attributed to the spirit of partnership. What is not often reported is that the success of the development stage is clearly based on the productive, focused, creative effort in the concept stage that began when the royal families of Denmark and Sweden finally agreed in 1990 to move ahead with a bridge project connecting their two countries. That SE effort shaped the approach to the project with well-defined time, budget, and quality constraints at the transition to the development stage. During the concept stage, the systems engineering team also recognized that the concerns of environmental groups would, and should, impact the approach to the construction of the bridge. The owners took a creative approach by inviting the head of a key environmental group to be a part of the board of directors. From the beginning of the development stage, the owners defined comprehensive requirements and provided definition drawings as part of the contract documents to ensure a project result that not only fulfilled the quality requirements on materials and workmanship, but also had the envisioned appearance. The contractor was responsible for the detailed design and for delivering a quality-assured product in accordance with the owner's requirements. The following are representative of the requirements levied at the start of the project. Schedule. Design life, 100 years. Construction time, 1996 to 2000. Railway. A railroad, International Union of Railways, UIC 71, with a train speed of 200 kilometers an hour. The motorway. A road axle load of 260 kilonewtons at a vehicle speed of 120 kilometers an hour. Ambient environment. Wind speed for 10 minutes is 61 meters per second. Wave height 2.5 meters. Ice thickness 0.6 meters. Temperature plus or minus 27 degrees Celsius. Ship impacts. The pylons 560 meganewtons to the girders 35 meganewtons. In addition to established requirements, this project crossed national boundaries and was thereby subject to the legislations of each country. Technical requirements were based on the Euro codes, with project-specific amendments made to suit the national standards of both countries. Special safety regulations were set up for the working conditions, meeting the individual safety standards of Denmark and Sweden. The railway link introduced yet another challenge. In Denmark, the rail traffic is right-handed, as on roadways where the trains in Sweden pass on the left-hand side. The connection needed to ensure a logical transition between the two systems, including safety aspects. In addition, the railway power supply differs between the two countries. Thus, it was necessary to develop a system that could accommodate power supply for both railway systems and switch between them on the fly. The design of a major cable-stayed bridge with approach spans for both road and railway traffic involves several disciplines, including, but not limited to, geotechnical engineering, aerodynamics, foundation engineering, wind tunnel tests, design of piers and pylons, design of composite girders, design of cables and anchorages, design of structural monitoring system, ship impact analysis, earthquake analysis, analysis of shrinkage and creep of concrete, ice load analysis, fatigue analysis, pavement design, mechanical systems, electrical systems, comfort analysis for railway passengers, traffic forecast, operation and maintenance aspects, analysis of construction stages, risk analysis for construction and operation, quality management, and environmental studies and monitoring. Comprehensive risk analyses were carried out in connection with the initial planning studies, including specification of requirements to secure all safety aspects. Important examples of the results of these studies for the Øresund Bridge were as follows. Navigation span was increased from 330 meters to 490 meters. The navigation channel was realigned and deepened to reduce ship groundings. Pier protection islands were introduced to mitigate bridge and ship accidents. Risks were considered in a systematic way using contemporary risk analysis methods such as functional safety analysis using fault tree and what-if techniques. Three main issues were considered under the design-build contract. General identification and assessment of construction risks. Ship collision in connection with realignment of the navigation channel. Risks in connection with 5-year bridge operation by contractor. A fully quantified risk assessment of the human safety and traffic delay risks was carried out for a comprehensive list of hazards, including fire, explosion, train collisions and derailments, road accidents, ship collisions and groundings, aircraft collisions, environmental loads beyond design basis, and toxic spillages. An example of a consequence of this analysis was the provision of passive fire protection on the tunnel walls and ceilings. Both Denmark and Sweden are proud of being among the cleanest industrial countries in the world. Their citizens, and therefore the politicians, would not allow for any adverse environmental impact from the construction or operation of a bridge. The Great Belt and Øresund Strait both constitute corridors between the salty Kattegat and the sweeter water of the Baltic Sea. Any reduction in water exchange would reduce the salt content and therefore the oxygen content of the Baltic Sea and would alter its ecological balance. The Danish and Swedish authorities decided that the bridge should be designed in such a way that the flow through of water, salt, and oxygen into the Baltic was not affected. This requirement was designated the zero solution. To limit impacts on the local flora and fauna in Øresund during this construction, the Danish and Swedish authorities imposed a restriction that the spillage of seabed material from dredging operations should not exceed 5% of the dredged amounts. The zero solution was obtained by modeling with 2 different and independent hydrographical models. In total, 18 million cubic meters of seabed materials were dredged. All dredged materials were reused for reclamation of the artificial peninsula at Kastrup and the artificial island Peberholm. A comprehensive and intensive monitoring of the environment was performed to ensure and document the fulfillment of all environmental requirements. In their final status report from 2001, the Danish and Swedish authorities concluded that the zero solution, as well as all environmental requirements related to the construction of the link, had been fulfilled. Continued monitoring of eelgrass and common mussels showed that, after a general but minor decline, populations had recovered by the time the bridge was opened. Overall, the environment paid a low price at both Øresund and the Great Belt because it was given consideration throughout the planning and construction stages of the bridges. 3.6.2.3 Conclusions. This award-winning bridge is the subject of numerous articles and a PhD thesis, where details of the construction history and collaboration among all the stakeholders are provided. This project provides a clear example of the benefit of a solid concept stage where the management team was able to resist the customer-driven temptation to jump prematurely into the development stage. I'm going to take a quick break here.
Mic off. Mic on. Mic off. Mic on.
Section 3.6.3 Case 3 Prototype System, the Super High-Speed Train in China. 3.6.3.1 Background. Shanghai Transrapid is the first commercial high-speed commuting system using the state-of-the-art electromagnetic levitation technology, or otherwise known as maglev. The train runs from Shanghai's financial district to Pudong International Airport, and the total track length is about 30 kilometers, or 20 miles. The train takes 7 minutes and 20 seconds to complete the journey, can reach almost 320 kilometers an hour, or 200 miles an hour, in 2 minutes, and reaches its maximum speed of 430 kilometers an hour within 4 minutes. The Shanghai Transrapid project cost 10 billion yuan, $1.2 billion US, and took 2.5 years to complete. Construction began in March 2001, and public service commenced on January 1, 2003. Critics argue that the speed over such a short distance is unnecessary and that the line may never recoup this cost. However, the speculation is that this is a prototype to gather operational data assessing the feasibility of a Shanghai to Beijing maglev train route. From this perspective, this project makes perfect sense. Prior to this installation, many countries had argued over the feasibility of maglev trains. They do not have wheels or use a traditional rail. Rather, powerful magnets lift the entire train about 10 millimeters above the special track called a guideway, which mainly directs the passage of the train. Electromagnetic force is used to make the train hover and provide vertical and horizontal stabilization. The frequency, intensity, and direction of the electric current in the track control the main train's movement, while the power for the levitation system is supplied by the train's onboard batteries, which recharge whenever the train is moving. Maglev trains do not have an onboard motor. The guideway contains a built-in electric motor that generates an electromagnetic field that pulls the train down the track. Putting the propulsion system in the guideway rather than onboard the trains makes the cars lighter, which enables the train to accelerate quickly. The super high speeds are attained largely due to the reduction of friction. Despite the high speed, the maglev system runs more quietly than a typical commuter train, consumes less energy, and is nearly impossible to derail because of the way the train's underside partially wraps around the guideway like a giant set of arms hugging the train to the elevated platform. Passengers experience a comfortable and quiet ride due to the maglev technology and the specially designed window. Noise level is less than 60 decibels at a speed of 300 kilometers an hour. The approach, section 3.6.3.2. The Chinese authorities considered the economical operation, low energy consumption, less environmental impact, and high speed when choosing a solution suitable for ground transport between hubs that range from hundreds to over 1,000 kilometers apart. But the same solution also needs to be suitable for modern mass rapid passenger transportation between a center city and adjacent cities. Despite the many advantages, in 1999, the technology was considered to be in an experimental stage. Its technological superiority, safety, and economic performance not yet proven by commercialized operation. The current line is the result of a compromise. It was built as a demonstration to verify the maturity, availability, economics, and safety of a high-speed maglev transportation system. The basic technology to create a maglev system has been around since 1979, but until this project, it had never been realized, mostly due to the expense of developing a new train system. Many experts believe that superfast steel wheel rail systems, such as those in France and Japan, have reached the limits of this technology and cannot go any faster. Maglev proponents describe the system as the first fundamental innovation in the field of railway technology since the invention of the railway, and are watching proposals for maglev installations in Germany and the United States. 3.6.3.3 Conclusions. From an SE perspective, this case illustrates the fact that a project that goes through all the stages from concept to operations may in fact simply be part of the concept stage of a larger effort. Let me take another quick break.
Mic off. Mic on.
Alright. 3.6.4 Case 4. Cybersecurity considerations in systems engineering. The Stuxnet attack on a cyber-physical system. 3.6.4.1 Background. As our world becomes increasingly digital, the issue of cybersecurity is a factor that systems engineers need to take into account. Both hardware and software systems are increasingly at risk for disruption or damage caused by threats taking advantage of digital technologies. Stuxnet, a cyber attack on Iran's nuclear capabilities, illustrates the need for systems engineers to be comprehensive in their assignment of vulnerabilities and rigorous in their mitigation of attack potential. This case study discusses a new degree of attack sophistication previously unseen, a new level of malware complexity at military-grade performance, nearly no side effects and pinpoint accuracy. However, though the creation and deployment of Stuxnet were expensive undertakings, the strategy, tactical methods, and code mechanisms are now openly available for others to reuse and build upon at much less expense. Cyber-physical systems attacks are becoming increasingly prevalent, and systems engineering must consider the implications of cybersecurity to reduce the vulnerabilities. Iran's Natanz nuclear fuel enrichment plant is a military-hardened facility with a security fence surrounding a complex of buildings, which are, in turn, protected by a series of concrete walls. The complex contains several cascade halls for the production of enriched uranium and gas centrifuges. This facility was further hardened with a roof of several meters of reinforced concrete and covered with a thick layer of earth. Each of the cascade halls is a cyber-physical system, with an industrial control system of programmable logic controllers, computers, an internal network with no connections to the outside world, and capacity for thousands of centrifuges. Though the internal network is isolated from the outside world by an air gap, possible vulnerabilities still include malicious insider collusion, non-malicious insider insertion of memory devices brought in from the outside, visiting service technicians, and supply chain intervention. It has been suggested that all of these breach vectors may have played a role in the massive centrifuge damage that began occurring in 2009 and continued at least through 2010. Malware, now known as Stuxnet, was introduced into the ICS of at least one of the cascade halls and managed to take surreptitious control of the centrifuges, causing them to spin periodically and repeatedly at rates damaging to sustained physical operation. The net effect of the attack is still unclear, but at a minimum, it ranged from disruption of the production process up to potential permanent damage to the affected centrifuges. The approach 3.6.4.2. Many characteristics of Stuxnet are unprecedented and stand as the inflection point that ushers in a new era of system attack methodology in cyber-physical system targeting. Illuminating forensic analysis of the Stuxnet code was conducted by several well-known cybersecurity firms, with detailed post-mortems covered in two documents from the Institute for Science and International Security. Did Stuxnet take out 1,000 centrifuges at the Natanz enrichment plant? And Stuxnet malware and Natanz update of ISIS December 22, 2010 report. This analysis is beneficial in expanding the risk landscape that systems engineers should consider during design. Below are some concepts that are concerned in the context of Stuxnet. Knowing what to do. Intelligence. To be successful, a threat has to be able to take advantage of the targeted systems. It is uncertain how the perpetrators knew what specific devices were employed in what configuration at Natanz, but after the Stuxnet code was analyzed, Natanz was clearly identified as the target. Stuxnet infected many sites other than Natanz, but it would only activate if that site was configured to certain specific system specifications. The perpetrators needed specific system configuration information to know how to cause damage, and also to know how to single out the target among many similar but not identical facilities elsewhere. Systems engineers need to consider that adversaries will attempt to gain intelligence on a system and must consider methods to prevent this. Crafting the code. A zero-day attack is one that exploits a previously unknown vulnerability in a computer application, one that developers have had no time to address and patch. Stuxnet attacked Windows systems outside of the FEP using a variety of zero-day exploits and stolen certificates to get proper insertion into the operating system, and then initiated a multi-stage propagation mechanism that started with a universal serial bus, removable media infected outside the FEP, and ended with code insertion into the ICS inside the FEP. Systems engineers need to be prepared for many different attack vectors, including internal threats, and must consider them during system design. Jumping the air gap. It is widely believed that Stuxnet crossed the air gap on a USB removable media device, which had originally been infected on a computer outside the FPP and carried inside. But it is also suggested that the supply chain for PLCs may have been at least one additional infection vector. Whatever the methods, the air gap was crossed multiple times. USB removable media could have also affected a bidirectional transfer of information, sending out detailed intelligence about device types connected to the FEP network, subsequently relayed to remote servers outside of the control of the facility. Systems engineers always need to remember that threats to the system are both inside and outside the system boundary. Dynamic updating. Analysis shows that the attack code, once inserted, could be updated and changed over time, perhaps to take advantage of new knowledge or to implement new objectives. Stuxnet appears to be continuously updated, with new operational parameters reintroduced as new air gap crossings occur. Systems engineers need to prepare for situations after a successful attack has occurred. 3.6.4.3 Conclusions. As the complexity and technology of systems change, the systems engineer's perspective needs to adjust accordingly. The increasing use of digital-based technologies in system design offers enormous benefits to everyone. However, the introduction of digital technologies also brings different risks than previously dealt with by systems engineering. The case study earlier illustrates a point in time behind us, and the adversarial community continues to evolve new methods. The lesson of this case study is that systems engineers need to understand the threats towards their systems, be cognizant that attacks can and will occur, and be proactive in protecting their systems. Robust and dynamic system security needs full engagement of systems engineering. A database that systems engineers should be aware of is maintained by the National Institute of Standards and Technology. And then 365 is the final one. I'm going to read this one a little bit quicker. And this is Case 5, Design for Maintainability, Incubators. Note, this case study is excerpted from Where Good Ideas Come From, The Natural History of Innovation. 3651, Background. In the late 1870s, a Parisian obstetrician named Stephanie Tarnier was visiting the Paris Zoo where they had farm animals. While there, he conceived the idea of adapting a chicken incubator to use for human newborns, and he hired the zoo's poultry raiser to construct a device that would perform a similar function for human newborns. At the time, infant mortality was staggeringly high, even in a city as sophisticated as Paris. 1 in 5 babies died before learning to crawl, and the odds were far worse for premature babies, born with low birth weights. Tarnier installed his incubators for newborns at Maternité de Paris, and quickly embarked on a quick study of 500 babies. The results shocked the Parisian medical establishment. While 66% of low-weight babies died within weeks of birth, only 38% died if they were housed in Tarnier's incubating box. Tarnier's statistical analysis gave newborn incubation the push that it needed. Within a few years, the Paris Municipal Board required that incubators were installed in all the city's maternity hospitals. Modern incubators, supplemented with high oxygen therapy and other advances, became standard equipment in all American hospitals after the end of World War II, triggering a spectacular 75% decline in infant mortality rates between 1950 and 1998. In the developing world, however, the infant mortality story remains bleak, whereas infant deaths are below 10 per thousand births between Europe and the United States. Over 100 infants die per thousand in countries like Liberia and Ethiopia, many of them premature babies that would have survived with access to incubators. But modern incubators are complex, expensive things. A standard incubator in an American hospital might cost more than $40,000, but the expense is arguably the small hurdle to overcome. Complex equipment breaks, and when it breaks, you need the technical expertise to fix it. You need replacement parts. In the year that followed the 2004 Indian Ocean tsunami, the Indonesian city of Niuloba received 8 incubators from a range of international relief organizations. By late 2008, when an MIT professor named Timothy Prostero visited the hospital, all 8 were out of order, the victims of power surges and tropical humidity, along with the hospital staff's inability to read the English repair manual. Muloba incubators were a representative sample. Some studies suggest that as much as 95% of medical technology donated to developing countries breaks within the first 5 years of use. 3652 Approach. Prestero had a vested interest in these broken incubators because the organization he founded, Design That Matters, had been working for several years on a scheme for a more reliable and less expensive incubator that recognized complex medical technology was likely to have a very different tenure in a developing world context than it would in an American or European hospital. Designing an incubator for a developing country wasn't just a matter of creating something that worked, it was also a matter of creating something that would break in a non-catastrophic way. You couldn't guarantee a steady supply of spare parts or trained repair technicians, so instead, Prestero and his team decided to build an incubator out of parts that were already abundant in the developing world. The idea had originated with a Boston doctor named Jonathan Rawson, who had observed that even the smaller towns of the developing world seemed to be able to keep automobiles in working order. The towns might lack air conditioning and laptops and cable television, but they managed to keep their Toyota 4Runners on the road. So Rawson approached Prestero with an idea. What if you made an incubator out of automobile parts? Give me 1 second. I need to do something here. Alright. 3 years after Rawson suggested the idea, the Design That Matters team introduced a prototype device called NeoNurture. From the outside, it looked like a streamlined modern incubator, but its guts were automotive. Sealed beam headlights supplied the crucial warmth. Dashboard fans provided filtered air circulation. Door chimes provided alarms. You could power the device via an adapted cigarette lighter or a standard issue motorcycle battery. Building the NeoNurture out of car parts was doubly efficient because it tapped both the local supply of parts themselves and the local knowledge of automobile repair. These were both abundant resources in a developing world context, as Rawson liked to say. You didn't have to be a trained medical technician to fix the NeoNurture. You didn't even have to read the manual. You just needed to know how to replace a broken headlight. Conclusions. 3653. Systems engineers need to consider issues like maintainability, producibility, and supportability at the project outset and the concept stage. It is too late to add these during the production stage. And that right there is the end of the case studies for Chapter 3.